Good morning, ladies and gentlemen. I'm Zheng from Nanjing University, China. Glad to have the opportunity to visit Korea in this beautiful season and give a presentation here. And so first of all, I would like to express my sincere thanks to Professor Park for your kind invitation. Yeah. Well, after so many device and industry-oriented presentation, my talk will focus on more basic one. Yeah, the title of my talk is the synthesis, structure, and properties of one-dimensional aluminum nitride nanostructured materials. But before I start to this issue, I would like to give a very brief introduction to the six-membered ring-based growth mechanism of carbon nanotubers with benzene precursor, since I think carbon nanotuber is also a very important display material. And the second, this issue is closely related to my next issue. Yeah. So. As we know, carbon nanotubers has become one of the most important advanced materials since 1991. Roughly speaking, a carbon nanotuber is a seamless tuber made of carbon atoms with diameters in nanometer range. Because of the nanotubular structure, many novel properties, for example, the superior mechanical, chemical, electronic properties has been gradually recognized, which makes carbon nanotubers have great potential applications in many fields. For example, in field emission display, nanoelectronic device, composites, gas storage, and so on. So carbon nanotube-related studies has become a worldwide interesting topic. Yeah. And great progress in the study on synthesis properties and applications of carbon nanotubers has been obtained. As we know, the growth mechanism is a very important issue, since it's not only scientifically interesting but also very useful for possible controllable synthesis of carbon nanotubers. However, today the growth mechanism is still a long-standing and controversial issue, and little has been learned about the chemistry involved. And in our synthesis of carbon nanotubers with benzene precursor, we get a rather good quality carbon nanotuber, and a very high yield data was obtained. The yield is usually larger than 500 weight%. In literature, it's usually less than 100 weight%. Yeah, and our high-resolution transmission electron microscopic characterization indicates that there are two typical ends of the products. The first one looks like this. The end was coupled by a catalyst. This is the corresponding EGS spectrum of this end. Indicates the iron nickel alloy catalysts here. And another end looks like this. It's closed end without catalyst. Now I will show you here again the data. Yeah. To my knowledge, this is the highest yield, or one of the highest yields to data. Yeah. Then question comes. Yeah. Why could it produce so high yields? Yeah. This will of course stimulate our imagination and or speculation. Yeah. As we know, there is a high structural similarity between benzene molecule and the graphene sheet. Yeah. As we know, the carbon nanotube is a long graphene plane. Yeah. You see the construction unit. Yes, the construction unit of the graphene is completely the same as the carbon-6 ring of the benzene molecule. Yeah, actually, the graphene sheet is constructed by such units. So it's possible if we could find a suitable catalyst to preferentially dissociate these carbon-hydrogen bonds, then it's possible to construct the carbon nanotubers with the carbon-6 ring as the building units. If the carbon-6 ring as a building unit, then the yield will be much higher, since usually carbon nanotubers was constructed by the atom by atom. Yeah, and this is by 6 atoms and 6 atoms. Yeah, and now further analysis indicates that there are two possibilities for the dissociation of the benzene molecule. The first one is the dissociation of carbon-carbon bonds along this line, yeah, and another line is another manner is the dissociation of carbon-hydrogen bond along this line, yeah. With this line, only hydrogen will be released in the preparation of carbon nanotubes. And with this line, you could detect some carbon-hydrogen species, for example, CH4, CH, and some other carbon middle products. Yeah, and as we know, the benzene carbon-6 ring of benzene is very stable. Yeah, and the bonding energy of carbon-carbon bond is 477.5 kJ per mole, and the carbon-hydrogen bonds have the bonding energy of 416 kJ per mole. So this is less than this carbon-hydrogen bond is less than carbon-carbon bond. So it's possible to dissociate. So the predominant dissociation of carbon-hydrogen bond of benzene is possible. So if this is really the case, what will happen? We could make a speculation. Yeah. So if the carbon-hydrogen bond is preferentially dissociated, then you could imagine, yeah, the benzene molecule will first absorb on the catalyst surface, and then aggregate to the graphene sheet. Yeah, you could look the below picture. Yeah, for example, the carbon-hydrogen bonds here were dissociated, and the carbon-hydrogen bond here were dissociated, and a new carbon-carbon bond will be built, and the similar case happened here and here. So the three benzene molecule will aggregate to the graphene sheet, and the further incorporation of the benzene molecule will increase the size of the graphene sheet. So then the graphene sheet were covered on the catalyst surface, and due to the increase of the strain energy, and it will precipitate to the tubular structure, and further incorporation of the benzene molecule into the edge will results in the growth of carbon nanotubes. Finally, carbon nanotube will be obtained. Yeah. And is this the real story? Then we make an in situ study on the CVD synthesis of carbon nanotubes with benzene precursor by thermal analyzer and mass spectral technology technique. Yeah. And the 5 is the thermal analyzer, and the 7 is the mass spectrometer, and the 6 is the capillary tuber. And the benzene molecule were introduced to the thermal analyzer. The catalyst was put into the oven of the thermal analyzer, and so the changing behavior of the catalyst and the weight gain during preparation could be monitored by the thermal analyzer, and the released gaseous species could be online analyzed by the mass spectrum, and by the integration of such related information, the growth mechanism could be figured out. Yeah, and here we use the iron cobalt, gamma aluminum supported iron cobalt as the catalyst, and this catalyst was obtained by heating the corresponding nitride. So originally it's oxide species. Yeah, in oxide state. Yeah. And I will not. This is the experimental procedure. I will not say it in detail. This is the products, and okay, this is the TG DSC profile of the preparation process, and also here is the mass spectral is the change of here is the results obtained from the mass spectrometer. I will not explain the experimental data in detail. Yeah, just the source. Yeah, and I will only tell you two facts. The first, yeah, we also do the same experiment without catalyst for comparison. Then the difference is that without catalyst, no gaseous species will be released. No carbon hydrogen species will be released. Also, no hydrogen will be released. And with the catalyst, only hydrogen will be released. Only hydrogen will be detected. Yes, this means only carbon hydrogen bonds was dissociated. And the second, you see this two curves. The first this one is corresponding to hydrogen, the changing signal of the for hydrogen, and this one is different DTG curve, corresponding to the growth of carbon nanotubers. You see these two curves resemble with each other in high degree, even in the even in the split details. The only difference is that the hydrogen curve is lags slightly behind the DTG curve. Yeah, this is very natural things you see. Since you see, the hydrogen will take a little time from the thermal analyzer to the mass spectrometer. So, the hydrogen signal lags slightly behind the carbon nanotuber. Yeah, yeah. And then, yeah. So by the integration of all the experimental data, we could get the six-membered limb-based growth mechanism. That's exactly what we expected. Yeah. The only difference is that since the catalyst, the original state of the catalyst is in oxide state, so there is reduction steps in at 640 centigrade. Yeah. Then we could detect a little carbon dioxide and water. Yeah. Since there is reactions like that. Oh yeah. And then if the according to this mechanism, so the final product will have the morphology of the will have the two ends. The first end have a catalyst, and another end is empty without catalyst. Yeah, this is really the case as we observed in our high resolution image. And high resolution image as we see here. Yeah. And a more lively schematic picture looks like this. Yeah. First, the benzene molecule will absorbed on the catalyst surface. Then, dissociation of hydrogen, and the hydrogen will be released, and the carbon-6 ring will aggregate to the graphene sheet, and then precipitate to tubular seeds, and the further incorporation of the benzene molecule to the edge will result in the growth of carbon nanotubers. Yeah. This is the story about the growth mechanism. Yeah. With experimental evidence. And now I will shift to the next topic about one-dimensional aluminum nitride nanostructures. As we know, the novel structure and the properties of carbon nanotubers stimulate the intensive exploration to the nanotubular geometry of other systems. And today the dozens of different nanotubers have been discovered. Here is a brief glance. Yeah, this is tungsten sulfur and molybdenum sulfur, and boron nitride and vanadium oxide and so on. Yeah, Indium phosphide, gallium nitride, and so on. And here is an incomplete summary. Yeah. You could see most of the nanotubers was constructed from the lead compounds, with weak van der Waals interaction between the layers. Yeah, and as we know, rolling up the stripe to form a tubular structure could result to opposite effects. First, the boundary atoms could be saturated. This is energetically favorable. Yeah. Second, a strain energy is introduced due to bending. Yeah, this is energetically unfavorable. So the final energy state of the nanotuber depend on the competition of these two facts. Yeah, and so for the layered compounds, due to the very weak interaction, due to the van der Waals force between the layers, between the molecule layers is very weak. So not not so large energy will be introduced for the bending. Yeah, since this band van der Waals force is very weak. Yeah, and so the evenly bent nanotubers could be relatively easily formed. Yeah, that's why we could prepare so many different kinds of nanotubers from lead compounds. However, for non-lead compounds, yeah, the chemical bond between the molecules is very strong. There is a chemical bond. Yeah, that means the van der Waals force was replaced by a chemical bond. Then the even bond like carbon nanotuber is impossible. Yeah, otherwise it's unstable due to the large strain energy introduced. Then what will happen? In 2003, Berkeley group synthesized the gallium nitride nanotubers. Yeah, these nanotubers were synthesized by an epitaxial casting approach using hexagonal zinc oxide nanowires as a template. As we know, the zinc oxide nanowire have such habits, crystal habits, and the epitaxial the gallium nitride on the surface of the zinc oxide, then remove the internal zinc oxide, so they could get the the nitride, gallium nitride nanotubers with hexagonal cross section. Yeah, this is very nature since the zinc oxide template have such morphology. Yeah, and in our synthesis, very simple synthesis. Yeah, by nitriding aluminum powder, with ammonia and nitrogen mixture. Yeah, faceted aluminum nanotubers have been used. It should be noticed that we make this experiment without a template. Yeah, with this, so it could reflect its crystal habits of aluminum nitride itself. Yeah, and here is some characterization results. Yeah, you see, the end of the aluminum for this nanotuber, it lies in such a fashion. Yeah, and you could see the right hand. Yeah. And for this nanotuber, it's lying in such fashion, yeah, in such fashion. So with the hexagonal cross section, the different lying fashion could also be reflected in the changing behavior of the construct along this line. Yeah. So and the further characterization, I will not explain in detail. Yeah, this is explanation of why the different lying fashion will show the different contrast for the nanotubers. Yeah. Well, so here's a high resolution transmission unit. This is the discovery of the aluminum nitride nanotubers. The importance is that the aluminum nitride is not a lead compound. That's a non-lead compound. So this nanotuber, the discovery of such kinds of nanotuber could extend the nanotuber structure from lead compounds to non-lead compounds. Yeah, and some new topics appears. Yeah, for example, what's the thermodynamic stability? What's the dynamic growth process, and what's its properties of such kind of structure of morphology? Yeah. And second, the nanotubers from other non-lead compounds will attract increasing attention. Actually, recently, there some new nanotuber structure from other non-lead compounds have gradually been reported. For example, this is TE nanotuber also with hexagonal morphology, and this is SE nanotuber, and this is zinc oxide nanotuber, also with a hexagonal structure, and this is cubic and gallium nitride, so it will have the rectangular cross section, and this is MgO, yeah, with rectangular with square cross section, yeah, and something like that, yeah. Well, Yeah, by changing the reaction temperature, we could also get some random or aligned aluminum nitride nanowires, and it looks like that. Yeah. This is a random aluminum nitride, and if we use the aluminum porous aluminum nitride, if we use the porous aluminum as a template, then we could align the nanowires in such a fashion. Yeah. As we know, the one-dimensional nanostructure is helpful for enhancing the field emission effect. Yeah. And also, aluminum nitride have a very small or even negative electron affinity. So both these effects is favorable for field emission. So maybe aluminum nitride is promising field emission materials. Yeah. So we measure the field emission property of the aluminum nitride nanowires. It's really it's comparable. It's comparable with the field emission property of carbon nanotubers. Yeah, we have make a comparison from the turning on field and the currents, something like that. Yeah, and by increasing the reaction temperature, the aluminum nitride nanobelts could also be obtained. Yeah, and but as we noticed that such morphology is usually in random form. Yeah, so we would like to align the aluminum nitride in a concept. We would like to align the aluminum nitride. So we use silicon as a substrate and coat nickel catalyst or first here, and then we use the ammonia and aluminum chloride as a precursor, and to grow the materials, and we found with this we found aluminum nanocores could in this condition aluminum nanocores could be obtained. Yeah, and this when changed. This is some morphology detail. Yeah, looks like this. Yeah. And if we change the reaction temperature from 700 centigrades to 800 centigrades, the tip it will change from the nanocore to nanocurrent. Yeah, to nanocurrent. And actually we have a discussion about the growth mechanism. Since the aluminum nitride species was formed in the catalyst, and it was diffused to in this direction with different concentration. Yeah, in upside the concentration of aluminum species will be small, and in the downside in the bottom side the aluminum species have large concentration, so it will show such it will form such a cone structure. And when increasing the temperature, the concentration difference in this direction were reduced. Yeah, so it will transfer to nanocurrents. Yeah, this is our explanation about the mechanism. Yeah, and then for this we also measure the field emission property, and it's the turn-on field is 12 volts per micrometer. Yeah, this is the data seems larger than carbon nanotubes, but actually in our reaction, in our case, yeah, the some voltage was applied into the resistance of silicon oxide resistance. So this is not the intrinsic property. I'm sure, yeah, the intrinsic turn-on field will be much smaller than this one. Yeah. So we are trying to improve the conducting property of the sample. Yeah. And as we know, yeah, the spin dot type of molybdenum and silicon cores is a milestone in the vacuum microelectronics. Yeah, usually such spin dot type nanocores was fabricated by up-down loops, yeah, from bigger to small, yeah, and now it's regarded that carbon nanotubes is best materials for field emission. For example, this is the carbon nanotube-based moving image of 9-inch FHDs made by Samsung, yeah, and in our case, yeah, these materials, the aluminum nitride nanocores, were produced by down-upper loops, yeah, from small to large, yeah, and this is a new system with such morphology and shows some promising field properties. So maybe it will have some application in field emission or in something like that, yeah. So finally, I will give a short summary. First, we have developed the 6-membered ring-based growth model of carbon nanotubes has been deduced. And second, aluminum nitride one-dimensional aluminum nitride structures, including faceted nanotubers, nanowires, nanobelts, nanocores, have been produced. And these systems have shown some promising properties in field emission. Yeah, thank you very much for your attention.